Hello guys, welcome to my channel Algorithm Avenue. In our previous video, we have worked on real world dataset, that is credit card customer churn prediction dataset. Now, similarly, in this video, we'll be working on another real world dataset, that is MNIST dataset. Okay, that is the MNIST dataset. The only major difference between the previous dataset and this dataset is it is a binary classification, and the dataset now we'll be working on is a multi-class classification dataset. Okay, this is a major difference between the previous dataset and the dataset that we are considering now. Okay, now let's see what's the MNIST dataset. Now in this MNIST dataset we have collection of 70,000 images, handwritten digit images. Okay, handwritten digit images, 70,000 handwritten digit images. Okay, each image is of size 28 cross 28. Okay, each image is of size 28 cross 28. Okay, each image is of size 28 cross 28, which means 28 rows and 28 columns. So in this image, okay, in this image the total number of pixel values are 28 cross 28, that is 784 pixel values. Okay, we have total of 784 pixel values. Okay, now our aim is to train our neural network on this dataset, and we have to make the predictions. Okay, and we have to make the predictions. Okay, now let's see how our artificial neural networks look like. Okay, now our first basic step is determining the number of inputs for our neural network. Okay, these are the number of inputs that we are considering for our neural network, that is 784. Okay, 784. Now this 784 is our input data, as we have total number of pixel values, that is 784. Okay, 784 pixel values. We'll be taking 784 inputs in our input layer. Okay, this is our input layer. Okay, we are taking 784 pixel values in our input layer. Now the next comes is an hidden layer. Okay, this is our hidden layer. Okay, this is our let me write it over here. This is our hidden layer. Okay, this is our hidden layer. Now in this hidden layer we are considering 128 hidden units. Okay, we are considering 128 hidden units. Okay, now this is our output layer. Okay, this is our output layer, which consists of 10 output nodes. Why 10 output nodes? Because in our dataset the digits are from 0 to 9. Okay, the handwritten digits are from 0 to 9, so we'll be getting 9 unique integers. So any image that goes into the neural network will be ranging from will be anything from 0 to 9. Okay, will be anything from 0 to 9. So we'll be considering 10 output nodes. Okay, we'll be considering 10 output nodes in our output layer. Okay, this output layer, the first node will be 0 and corresponding will be 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8 and 9. Okay, these are the total number of output nodes in our output layer, and this is the corresponding hidden layer, and this is the input layer. It is a two-layered neural network. The neural network that we are considering is a two-layered neural network. Okay, now this is the entire intuition on the dataset and the neural network that we are considering to solve this particular dataset. Okay, to solve this particular dataset. Now let's jump into our desktop to work on this MNIST dataset.
In the previous section of the video, I hope you guys understood the intuition on MNIST dataset. Okay, in this section of the video, our basic task is to our aim is to build an artificial neural network that can efficiently make predictions on the MNIST dataset. Okay, for that, first our task is to import the dataset from an external source to our Google Colab. Okay, so for that we are importing torch library. Okay, why torch library is imported is generally in PyTorch framework we work on tensors, right? In PyTorch framework we work on tensors. Okay, what this torch library does is it is used to efficiently work on tensors. Okay, it is used to efficiently work on tensors. So that is why import torch library. Now in the second part of the code, okay, in the second part of the code we are fetching OpenML website. Okay, OpenML is an online platform. Okay, OpenML is an online platform. In that online platform we have n number of datasets. Okay, n number of datasets, around 5k plus datasets. Okay, 5k plus unique datasets which are used for machine learning tasks. Okay, which are used for machine learning tasks. Okay, from that website we need to import our required dataset, that is MNIST dataset. Okay, once I'll show you the OpenML website. Okay, this is the OpenML website interface. Okay, this is the OpenML website interface, and these are the n number of datasets that are present in the OpenML website. Okay, these are the n number of datasets. If you want, you can work on this n number of datasets. Okay, now we have fetched the OpenML website. Okay, now after going through the OpenML website, what we need to do, we need to import from that OpenML website we need to import MNIST dataset. Okay, from that OpenML website we need to import the MNIST dataset into our Google Colab. Okay, so for that fetch OpenML MNIST dataset. Okay, in this part of the code we are importing MNIST dataset. Okay, to where we are importing the MNIST dataset? To our MNIST object. Okay, we are importing the MNIST dataset from the OpenML website to our MNIST object. Okay, this is the object I have created. This is the MNIST object I have created from the OpenML website. We are importing it to MNIST object. Okay, why we have put as frame is equal to false is when it is true the imported data is of data frames. Okay, data frames. Okay, the imported data is of data frames, but generally while working it is comfortable to work on numpy arrays. Okay, instead of working on data frames it is comfortable to work on, okay, it is comfortable to work on numpy arrays. So that is why we have made as frame is equal to false. Okay, for that purpose we have made as frame is equal to false. Okay, after making this false, what we have done is we have sent our MNIST data into x and y variables. Okay, x and y objects. Okay, x and y objects, we have sent the MNIST data. Okay, what the data present in the MNIST dataset we have sent into x and y. Okay, what we have sent into x? We have sent into x the data, the entire data present in the, okay, the entire data means the features. Okay, the pixel values that are present in the data we have sent into x, and the target values that are present in the data we have sent into y. Okay, that we have written over here. Okay, what are these pixel values? These are the pixel values. Okay, these are the pixel values that we have sent into x. Okay, for this corresponding pixel values, for this corresponding 784 pixel values will be having a corresponding numeric, right? Okay, generally now for this data, okay, these are our pixel values. For this pixel values will be having a corresponding data, right? Corresponding target. Okay, for this pixel values the corresponding target value is 5. Okay, for this pixel values the corresponding target value is 5. Now we have sent this entire data into our x variable, we have sent into our x object, and the target value, that is 0 to 9, that is 0 to 9 we have sent into y. Okay, in this way we have divided our data into okay, we have divided our data into data, that is features. Okay, in general terms it is called as features, but in this case it is called as data, and we have sent our target into y. So successfully sent our data into x and y objects. Now let us check the shape of the x and y objects. Okay, when you write x dot shape and y dot shape, it outputs the corresponding shapes of the x and y objects. Okay, now the shape of the x object is 70,000, that is 7. We have in MNIST dataset 70,000 images, right? We have in MNIST dataset we have 70,000 images. Now each image has corresponding different pixel values, right? Corresponding 784 different pixel values, right? Now let us say we have first image, right? First image we have this data. Okay, now for the second image we will be having some other data. Okay, entirely different data. Okay, in this way we have 70,000 images and 784 our total pixel values. Okay, 784 are our total pixel values, that is the shape of the X, and Y is we have 70,000 again for this corresponding 70,000 different pixel values, that is 70,000 different images will be having corresponding target values. Okay, that we are storing in Y. Okay, that we are storing in Y. So the output is 70,000. Okay, now let us see x. Okay, now let us see the data in X at 0th index. Okay, at 0th index we'll see the data. Okay, this is the data that is in the 0th index. Okay, this is the entire data. We'll be having around 784 pixel values in this. Okay, we'll be having 784 pixel values in this X of 0. If you take X of 1, okay, X at index 1, you will be having another set of pixel values. Okay, these are the entire data that is present in X of 0. Okay, now let us print the Y. Okay, now for this corresponding 784 pixel values we'll be having corresponding Y values. Okay, corresponding target values, that is first value is 5, second is 0, third is 4, and so on up to we'll be having 70,000 different, okay, 70,000 target values. Okay, the data type is object data type. Okay, the data type that is default in the data set is object data type for Y. Okay, now in the next part of the code what we'll be doing is we'll be splitting our data into training and testing. Okay, generally to attempt an exam, first you initially take training, right? You initially take training to attempt an exam. Similarly, for a model to make predictions, it also needs some kind of training, right? It also needs some kind of training. So for that training we need some corresponding data. So for that what we are doing is what we are doing in this code is we are splitting our data into training and test split. Okay, how we are splitting from sklearn.model selection import train test split. Okay, now to this train test split, okay, what we are splitting X and Y. Okay, X and Y objects, right? Okay, the data in X and Y we are splitting. Now X and Y is splitted into X train X test and Y train Y test. Okay, X is splitted into X train X test, Y is splitted into Y train Y test. Now what is the test size that I took is 0.142. Okay, you can take any data. Okay, you can take any test size. Okay, it may be 0.2, 0.3. Okay, better to take between 0 to 0.3. Okay, what I have taken is 0.12 and my random state is 42. Now here I am printing the corresponding shapes. Okay, now what I got is in Xtrain I got around 60,060 images and 784 pixel values, and in the Xtest I got 9,940 and 784 pixel values. Now in the Ytrain I got 60,060 pixel values, sorry, 60,060 images, and in the Ytest I got 9,940 images. Okay, in this way I have split my data into Xtrain Xtest and Ytrain Ytest. After we split the data, let us see how our data looks like. Okay, so for that we have imported MATLAB library, okay, matplotlib library, okay, to display any kind of images we generally import matplotlib library. So I imported matplotlib.pyplot as plt, and in matplotlib we have imshow. Okay, imshow which helps us to display the images. Okay, which helps us to display the images. Okay, so I have accessed it by plt.imshow. Okay, what I am sending into imshow, extend at the 0th index. Okay, extend 0 index I am sending into, okay, extend at the 0th index I am sending it to imshow to display the image. Okay, I have reshaped into 28 cross 28, means we will be having 28 cross 28. Okay, 28 cross 28 columns. Okay, in this way I have displayed my image. Okay, in Xtrain at 0th index, I have 0 image. Okay, I have target as 0 value. Okay, so it has outputted the output as 0. Okay, it has displayed the 0. Okay, now let us check the data types of Ytrain and Ytest. Okay, generally when we have checked the data type of Y, it is object. Okay, now now to work on the now for a PyTorch, now for a model to work on the data that is present, it must be numerical values. Okay, for our data, for our model to work on the data, it must be numerical values, but here we have object data type. Okay, now our y is in object data type, so our aim is to convert the object data type to numerical data type. Okay, our y is generally object data type, so what happens is our model will display an our model displays an type error. Okay, our model displays an type error. So to overcome that error, what we need to do is we need to do an type conversion from object to numerical data. So in this part of the code, I have transformed my labels from object to numerics. Okay, now my ytrain and ytest are transformed to objects to numerics. Now in this part of the code, what we are doing is, generally when you see in our previous project as well, what we have done is we have converted the numpy arrays to tensors. Okay, now we have converted the numpy arrays to tensors. Why? Because our PyTorch generally works on tensors. Okay, default data type is tensors. So in the similar way, we will be converting our extend and extest and ytrain and ytest to tensors, and from tensors to the data types. Okay, in the similar way we have converted extend to tensors, and from tensors to we have taken float32 as our data type, and extest to we have converted to tensors, and from tensors to we have taken float32 as our data type. Similarly, ytrain we have converted it to tensors, and we have taken the data type as long. Similarly, ytest we have converted to tensors, and from tensors to our data type long. Okay, in this way we have did a conversion of our data type from numpy arrays to tensors. Okay, now our next process is we need to scale our data. Similarly, we have seen in the previous project as well, we have scaled our data. Okay, it may be any type of scaling, but the entire data must be in between 0 to 1. Okay, entire pixel values must be in between 0 to 1. So we need to scale our data. Now first let us see how our data is looking. Okay, this is our data format. Okay, this is our data format, and the pixel values are very high. Okay, our pixel values are very high. What happens when we have this higher pixel values is our weights and bias doesn't converge much easily. Okay, doesn't converge much easily to produce local minima. Okay, to produce loss to global minima. Okay, our loss doesn't converge to global minima that easily. So what we do is, instead of working on this higher pixel values, we scale them. Okay, we scale them by dividing it with the highest pixel value. Okay, we are dividing here with the highest pixel value. Generally in grayscale images, the highest pixel value is 255. Okay, in grayscale images, the highest pixel value is 255, and the lowest pixel value is 0. Okay, now when we divide with the highest pixel value, what happens is the highest pixel value in the images may be 255. When you divide it with another 255, the 255 pixel value will be converted to 1. Okay, now the 0 divided by 255 is 0. Okay, now any kind of pixel value you take, it will be in between 0 to 1. So you have converted your extend and extest between pixel values between 0 to 1. Okay, till this step what you have done is you have first imported the data to your PyTorch library. From after importing it to PyTorch library, you have split into train and test splits. Okay, after that you have pre-processed your data. Okay, you have readied your data so that it can pass easily through the neural networks. Okay, till this step you have entirely pre-processed the data, and now it's our turn to build our neural network. This is the neural network that I have built to work on the MNIST dataset. Okay, let us see how our neural network looks like. Okay, from torch import nn. Why we have imported nn is, it helps in building the custom neural networks. Okay, it helps in building the custom neural networks. After that, I have built a class with name MNIST dataset. Okay, with name MNIST dataset, which is subclassing nn.module. Okay, this name could be this name can be anything. Okay, you can give it yourself. I have just given the MNIST dataset. Okay, I have just named it MNIST dataset. Okay, now I have built a constructor which has default argument self and three other arguments, that is input features, output features, and hidden units. Okay, I have again written super.init to for handling the trainable parameters, for handling the trainable parameters in our neural network. Okay, now self.linear model, this I have named it as a linear model. It can be anything. Okay, you can name it anything. Okay, self.linear model is equal to nn.sequential. Okay, what this nn.sequential specifies is, generally it helps in the flow. Okay, it helps in the order of flow. Okay, order of flow of our input data into our neural networks. Okay, generally our order of the flow of the input to our neural networks will be, first will be our input layer. From input layer we'll be getting our data, then to our hidden layers to another hidden layers. Okay, so and till n number of hidden layers, and then our output layer. Okay, this sequential, what it does is it helps in sequential flow of the input data. Okay, sequential flow of the input data, like from hidden layers to next hidden layer. Okay, this hidden layer to this hidden layer, and then to the output layer. Okay, now nn.linear is our first layer. Okay, this is our first layer. Okay, with arguments as input features and hidden units, and the activation function of that layer, and the activation function of that layer is relu activation function. Okay, we are using the relu activation function for our first hidden layer, and this is our output layer. Okay, it is generally a two-layered neural network. Okay, we have built a two-layered neural network with one hidden layer and one output layer. In our first hidden layer we are using relu activation function. Okay, in the second hidden layer we are having, okay, this is our output layer. Okay, this is our output layer. Okay, now we are calling the forward method to flow of the to pass the inputs through our model. Okay, forward propagation. Now this MNIST dataset, okay, the class we have created here, we are calling it over here. Okay, this is our object. Okay, this is our model object. Okay, that is model 1. Okay, I have named it as model 1. This is our model object, and in that model object we are storing our entire dataset. Okay, we are storing our entire neural network in that model.1. Okay, MNIST dataset is equal to 784. Okay, this 784 are inputs. Okay, this 784 are inputs. Okay, and this 10 are our output nodes. Okay, we'll be having 10 output nodes, and in the hidden layer we'll be having 128 hidden units. Okay, 128 hidden units in our hidden layer, and we'll be having 10 output nodes in the output layer, and we'll be having 784 inputs. Why 784 is, generally our how our image looks like is, it will be of 28 cross 28 image. Okay, 28 cross 28 image. Now well, applying the flattening operation, generally when you take an image from the external sources, when you take the image from the external sources, it may not be flattened. Okay, it may not be flattened. It may be some 70,000 comma 28 cross 28. Okay, in that case what you need to do is, you need to add an flatten layer over here. Okay, at this point, okay, initially you need to add an flatten layer. Then after adding flatten layer, what happens is, each row will append corresponding, okay, horizontally along the axis 1. Okay, along the axis 1, each row will be appending correspondingly. Okay, each row will be corresponding appended corresponding. How many rows will be appended? 28 rows will be 28 rows will be appended, because we have 28 rows in our 28 cross 28 image. So in this way, when we flatten, we'll be getting 784 unique pixel value. Okay, 784 pixel values. Okay, that is why we have taken 784 inputs. Okay, that is why we have taken 784 inputs, and we have 10 output nodes and 128 our hidden units, and this is our model 1. Okay, we have created model 1 object. Okay, this is a summary of the model 1. Okay, now our next step is to take a loss function and optimizer. Okay, the loss function that we are using is cross entropy loss. Okay, cross entropy loss is our loss function. Generally while working on multi-class classification problems, we use cross entropy loss, and when we are working on binary classification problem, we use an binary cross entropy loss. Okay, binary cross entropy loss, or BCE with Logit's loss. Okay, these are the three major loss functions that we'll be generally using. Okay, as we are working on multi-class classification data, we'll be using cross entropy loss, and the optimizer that we are using is Adam optimizer, and our learning rate is 0.01. Okay, you can keep it as yourself 0.001, or it can be anything. Okay, this is our accuracy function. To measure the model accuracy, we use this accuracy function. Means how accurate our model is, we use the accuracy function. Okay, now in this step we are creating the training and testing loops. Okay, in this step we are creating the training and testing loops. Okay, now this part is our training loop. Okay, from here to here is our training loop, and from here to here is our, okay, sorry, from here to here is our testing loop. Okay, in our training loop, first we are setting our model 1 into training mode. Okay, first we need to set our model to training mode, then we need to calculate our y-logits. Y-logits are the raw outputs. Okay, y-logits are our raw outputs of the model. Okay, we are sending extend directly into our model 1, and it's omitting this y-logits. Okay, now loss is calculated between y-logits and y10. Okay, this y-prits are calculated by applying the softmax operation. Okay, softmax activation function. Okay, softmax activation function. Okay, you may have got and doubt that why we have not applied an activation function while building the model. Okay, here why didn't we apply the activation function is we are applying it over here. Okay, we are applying it over here. Okay, how these outputs are okay, how we are getting these outputs is, as we have 10 output layers. Okay, we have 10 output nodes, right? In our output layer we have 10 output nodes, right? Now each node will omit an prediction. Okay, predicted value. Each node will omit an predicted value. Now what we need to do is we need to pass this predicted value to the softmax activation function. After passing it through the softmax activation function, we'll get another set of predicted values. Now we'll be applying argmax operation on this probabilities. We'll be applying argmax operation on this predicted probabilities. Okay, now the maximum value that is omitted will be our y-pred. Okay, now loss is calculated between y-logits and y-train. Loss is calculated between y-logits and y-train, and accuracy is calculated between y-train and y-preds. Okay, here we are setting our gradients to 0, and here this is our back propagation step. Okay, this is our back propagation step, and here we are calculating our, here in this step we are calculating our, in optimizer dot step we are calculating our model parameters, and this model parameters are applied to the, okay, this newly obtained model parameters are applied to the next epoch. Okay, this fresh parameters are applied to the next set of next epoch. Okay, now we are setting it to evaluation mode. We are setting our model to evaluation mode. Okay, this entire is our testing. Okay, this entire is our testing. We are setting our model into evaluation mode. Okay, with the torch.inference mode is inference mode. Okay, inference mode is nothing but testing mode. Okay, why we write this specific code is, now generally our weights and biases are calculated at time of training. Okay, our weights and biases are calculated generally at the time of training, right? Okay, now it is not required for us to calculate weights and biases again at the time of prediction, right? Already calculated weights and biases are already available. Okay, already we have the availability of the weights and biases that are calculated at the time of training, so that weights and biases value are fixed. Now this fixed weights and bias values are used in the time of prediction. Okay, used in the time of prediction. Okay, now these are our, similarly we are calculating the test logits and test loss and y-preds, and this is our test accuracy. Okay, so this is our entire testing loop. Here we are printing our model results. Okay, here we are printing our model results. Okay, when you observe model results initially at the zero epoch, our training accuracy and testing accuracy are little bit low. As the epochs increases, our model is starting to learn, and we have achieved an accuracy of 91%. Okay, an accuracy of 91% in both training and testing. Okay, by this you can understand that model is learning very efficiently. Okay, these are our model results. Now in this set of code we are printing our model weights and weights and biases. Okay, model 1, okay, model dot static, generally model dot static is used to print the, okay, used to print the weights and biases of the model, weights and biases of the model. Okay, in the first layer these are a total set of weights. Okay, in our first layer these are our total set of weights, that is 784 cross 128. Okay, we'll be having 784 cross 128 weights, and these are a 128 bias. Okay, these are a 128 bias. This entire is corresponding to our first layer. Okay, this entire is corresponding to our first layer. Now when it comes to second layer, it will be 128 cross 128 cross 10. Okay, it will be 128 cross 10, and we'll be having corresponding 10 biases. Okay, this is our second layer, this is our first layer, and this is our second layer parameters. Okay, these are our total. To calculate the total number of trainable parameters in our model, we use this set of code. Okay, now let's make now we have entirely built our model, and we have also got an accuracy of around 91%. Now let's test our model. Okay, how do we test our model is, we'll be sending an value. Okay, we'll be sending some set of data. Okay, we'll be sending some set of pixel values. Okay, 784 pixel values to our model 1. Okay, our model 1 omits some 10 probabilities. Okay, after omitting the 10 probabilities, we'll be taking maximum. Okay, we'll be taking maximum of those probabilities, and we'll be seeing the output. Okay, and we'll be observing the output. Okay, now let us say we have sent x train of 0th index. Okay, 0th index, what data we have, okay, what pixel values we have sent to our model. Okay, we have sent to our model. Okay, it has omitted some 10 prediction probabilities. Okay, some 10 prediction probabilities. Now what we'll be doing is, okay, as I told in the previous step, we generally apply, okay, argmax operation. We generally apply argmax operation. Okay, and we have applied the argmax operation, and we have got an output as 0. Okay, 0 means for the data at the extent of 0, we have got the output, predicted output as 0. Okay, now let us see the by comparing it with the outputs. Okay, comparing it with the outputs of each node. Okay, for the first node we have got something around 11. This is our second node output, third node, fourth, fifth, sixth, seventh, eighth, ninth, 10th. Right, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, for 9 output nodes we have got 9 prediction probabilities. Now we are taking the maximum. Okay, now for the first node, that is 0 node, we have got the output. Okay, we have got the maximum value, so output is 0. Okay, now when you want to compare the predicted output by our model is correct or not, in ytrain we have our prediction probabilities. Okay, in ytrain we have our true labels, right? In ytrain we have our true labels. Now let us print the true labels and compare the model results. Okay, for xtrain of 0, our output will be ytrain of 0, right? Okay, ytrain of 0th index. Okay, xtrain at 0th index will be having output as ytrain at 0th index. Now at 0th index, what is the output, what is the label we have? 0. Okay, our model has also outputted 0. Okay, now let us take 1. Okay, now let us take 1 and run this cell and run this cell. Okay, it has outputted 5. Okay, it has outputted 5. Our true output is also 5, means our model is working fine. Okay, in this way we have built an entire model. Okay, we have built a model to make predictions on the MNIST dataset. Okay, and finally we have achieved some good results. Okay, we have achieved some good results. Okay, this is a basic project that I have explained you to understand the entire set of theory concepts that we have discussed till now. Okay, you need not remember the entire code, but just try to understand how the flow is working. Okay, how the flow is working, how we are building the model. Okay, finally we have succeeded in building our model. Okay, if you like the video, please like, share and subscribe.